So we're done all the simple harmonic motion stuff now, okay? And we're moving on to looking at waves. And the reason waves and simple harmonic motion go in the same unit is because waves are caused by something oscillating with simple harmonic motion in a medium that can be disturbed, okay? No. No, it causes tides. That's different. No, they're not the same thing, okay? All right, so a wave, okay? A wave is nothing more than a traveling disturbance. Okay? In order to make a wave, you have to disturb a medium. Okay? All waves, with the exception of light, require a medium in which to travel. Okay? Light is the exception because of the wave-particle duality of light. That is, wave is both a, or light, sorry, is both a wave and a particle. It's kind of its own medium. And so, yeah, it's weird. But, okay, all other waves require a medium in which to travel, which is why in space no one can hear you scream. Unless you have a radio. Then you can scream over the radio. Okay? But if you don't have a radio and you get out into space without a suit on, you can scream all you want, but you won't make any noise. Okay? And the reason for that is your vocal cords do not have any air to vibrate in. Okay? When we speak, our vocal cords vibrate back and forth. They disturb the air around them. That sound travels outwards, okay? And people can detect it. If you throw a rock into the water, you disturb the water with the rock, okay? And you see the waves travel away from that, okay? You've disturbed a medium somehow, okay? And waves are created as a result. Now, when you throw a rock into the water, do you get more than one wave? Why? You only disturbed it once. Well, actually, it's the elastic nature of the water, okay? And when the rock goes through it, the water rebounds. There's kind of an elastic rebound effect because of the hydrogen bonds and that polar nature of water stuff. So it kind of does this, and so it continues to oscillate even after the initial disturbance. Okay, obviously the oscillations decrease more and more each time. But yeah, I mean, if I make a sound wave, if I just go, okay, it doesn't keep like clap, 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 clap. It's not echoing, right? It's not doing something like that. Okay, I only get one disturbance there. The air isn't an elastic medium like water is. Okay, so I only get that one single sound. An echo is just a reflection. So if you shout at a cliff, you'll look crazy. Okay, but it bounces off the cliff and just comes back. So all you're hearing, it's just like when you look in a mirror. Looking at your reflection in a mirror is an echo of light as opposed to sound. So like when you're talking, it doesn't like it does. That's why you sound different in your own head than you sound if you listen to a recording of yourself. Ever do that? I do it all the time because I do this. I'm like, man, people have to listen to that because I sound so cool in my own head. Okay, but when I listen to recordings of myself, I'm like, oh man, I have this awful voice. Okay, but yeah, we sound different because what we hear is a combination of resonance within our sinus cavities and reflections off of other things within the room. Okay, so it sounds a little different to us than it does to people hearing the waves directly. Yeah. Okay, so we're going to look at two kinds of waves in the wave unit: transverse waves and longitudinal waves. That is not spelt incorrectly. That is how longitudinal. Longitude are lines on a map. This is not. Okay. So the way you do self-recording, is that the exact same way you do? Yes, but it's much more true. Yeah. Yeah. Oh, I know. It's disconcerting, right? Okay. All right. So transverse and longitudinal waves are slightly different. Okay. They're different in that it's the way the medium moves as opposed to the way the wave moves. All right. If I make like a disturbance in water, I make transverse waves. I disturb the water up and down. The waves travel outwards. Okay. So the movement of the water is up and down, but the waves travel horizontally outwards. They're perpendicular or transverse to each other. Okay. So in a transverse wave, the direction the medium oscillates is perpendicular to the way the waves travel. In a longitudinal wave, they're parallel. Okay? Sound waves are longitudinal waves. If you've ever watched a subwoofer, okay, they go back and forth like this, okay, and they move the air. Okay? So they disturb the air back and forth, and the waves travel parallel to that, horizontally. Okay, so that's the difference between a transverse and a longitudinal wave. It just has to do with the way the medium moves in relation to the way the wave moves. Okay. All right. We need to understand how waves are created and propagated. Okay. Well, we've already said for a wave to be propagated, it has to have a what? A medium. There has to be something for it to travel in, and for it to be created, we have to disturb that medium. That means that in order to make a wave, we have to do, starts with W, four-letter word, work. Yeah, okay. Energy is required to make waves. Okay, I have to disturb a medium. I have to exert a force through a distance. I have to push on it, pull on it, whatever, okay, in order to get that wave going. All right, so waves transfer energy from place to place. Okay, and if we didn't realize that before, just think about, if you've been out on the ocean, okay, or even on a lake, somebody goes by and makes waves. Do you go up and down? Yes. Okay. The only way you go up and down is if the waves can transfer energy to you and lift you up and bring you back down. Okay. They're transferring energy, okay, through a medium to other places. Okay. In order for your eardrum to vibrate back and forth, waves have to travel there and hit your eardrum and make it move back and forth. Okay. Everybody with me there? Yeah. What if the wave has lots of energy? Can it do a lot of work? Like a tidal wave? Yeah. Okay. Tidal wave can do a lot of work. Okay. Same with really loud sounds. Okay. They can damage your eardrum. Right. This is something your generation is going to know way more about than any generation previous to you. Okay. Because you guys are the iPod generation. Okay. You guys have access to way better music technology, way better earbuds, big headphones, whatever, than we ever had. Right. My generation had the Sony Walkman. Right. This yellow brick that you carried around. You put 4 AA batteries, listen for about 90 minutes, and then put 4 more AA batteries in it. Okay, yeah, because it had to turn the tape. We used tapes. Yeah. So anyway, yeah, your technology is way better, but our headphones, they were like these orange foam things that sat on the outside. Okay, most anybody could hear what you were listening to because they didn't channel the sound directly into your ear, which is what the stuff you guys have does. Okay, it does a much better job of channeling sound into your ear, and that means that it has the potential to hurt your eardrums and your hearing a lot more than the stuff we had. Okay. So keep that in mind when you're listening to your music. I think actually Apple with their last set made it so that you couldn't make more than 90 decibels with their stock earbud headphones, so that because they were seeing into the future and knowing they were going to have lawsuit after lawsuit if they didn't do something. Okay, but yeah, if you have really powerful headphones, you could be doing damage to your eardrum because anything over 90 decibels causes permanent hearing loss. Okay, not immediate, not like significant, but it's repeated exposure. Okay, the more you expose your ears to sounds over 90 decibels, okay, the more damage you do. So, if you're that kid who walks down the hall and I can hear every lyric of the song you're listening to through your headphones when I'm sitting at my desk with the door shut, okay, because we had a kid like that about 10 years ago. Okay, like that's how loud he was. I don't know, he's got to be deaf now. Okay, but yeah, he's got to be deaf now. That's how loud his headphones were. Okay, I'm not kidding you when I say I was sitting at my desk with the door shut, could hear every lyric, and they weren't nice either. Yeah, that he would listen to. Well, if you have a sound meter, but usually a good indication is if you take the hearing, like the buds out, and yeah, your ears are ringing, or you get that sensation of like water rushing into your ear, like kind of that, or pressure. That's usually a sign that, yeah, that's what you've done. Okay. To give you an idea, like right now, my voice would be somewhere between 60 and 70. You know what? Let's do this. If you're listening to your headphones really, really loud, okay, what they're causing your eardrum to do is move further than it should. Okay, on the back of your eardrum, and you probably know it's like grade 5 science, right? The parts of the little bones in the middle ear, right? You got the hammer, the anvil, and the stirrup. Okay, the malleus, the incus, and what's the other one? Anyway, so those bones are joined together like any two bones in your body are joined together. They're joined together by ligaments and tendons, but they're really, really small. Okay, so if you make your wrist or your ankle or your shoulder move further than it's supposed to, it gets sore, right? You injure or sprain the ligaments and tendons and it swells up and it's sore for a while. That's what, when your ears are ringing, that's what's happened inside your ear. You've essentially sprained the tiny little ligaments that attach to those tiny little bones that are attached to your eardrum. Okay, and so you get that ringing in your ears. That's the result of inflammation. Okay? In the same way that your ankle swells up or your wrist swells up when you injure it, those swell up. And they move more freely then, just like your joints do if you injure them, right? When they're swollen, they're not as strong, okay? That same thing inside. So you move your head, they move. And then when they move, they tell your brain that it's hearing stuff, even though you don't. Okay, that's different from the voices in your head, by the way. Okay, if you hear those, you got other problems. But okay, this is just the ringing in your ears. Okay, and that's just the result of inflammation in there that's causing them to basically send false messages to your brain. But it is a sign that you have caused damage to those bones. Now, what happens is over time, and this happens in any joint in your body, if you repeatedly injure it, scar tissue builds up. Okay, the scar tissue builds up and then it can become very fibrous and it can reduce the mobility of the joint, including the ones in the ears. And you can't just go to physio for the ones in your ears. Okay, so you get this fibrous kind of scar tissue buildup over those, and you start to get a narrower and narrower range of sounds that you can hear. Okay, and it starts out at either end. Okay, you don't usually lose the stuff that's kind of, where people's voices are and such. Okay, you don't lose that right away, but you'll start to lose the soft sounds. So S's and F's and things like that will be the first things you notice you don't hear as well. Okay, and things like that. But it will start to narrow. Okay, the more you damage it, the narrower your bands of hearing become. Okay, yeah. So you want to watch that, because as soon as it starts getting into normal speech range, then you're gonna notice it, and by then it's pretty late actually.
So it doesn't have to do anything with your actual brain degrading, like your
No.
like the processing of the brain.
No, it's the mechanical part that's failing. Yeah, not the nerve part. The nerve part can be more damaged by like a sudden rupture, right? Like then you could damage that part, but most of the time anything to do with that is more congenital, right? Like you're born with it. Like my son, he's got the same problem. He's got some malformation of the bones in the middle ear, so there are sounds he doesn't hear, so he wears hearing aids because of that. But it was congenital as opposed to it was something that happened to him. Right?
So I have two questions. First, what do hearing aids do? And for a deaf person, what's wrong with it?
Well, again, there's lots of things that can cause deafness, right? The hearing aids, and again, it depends on what type of hearing aids you have. Like my son just wears hearing aids that amplify the frequencies he doesn't hear. So when he wears them, there's settings that they have to calibrate at the hearing place, and so the microphone picks up the sounds, it amplifies the sounds that are in the ranges he doesn't hear, and then he hears more normally. They can also filter out background sounds. Like the technology for hearing aids is getting really good. Like it's got new noise filtering stuff that's just incredible. But yeah, that's essentially what they do. If deafness can be caused by any number of things. It could be a congenital thing where it's a nerve induction thing. It can be like my son's, it's a malformation of the bones, so they don't transfer certain frequencies very well. There's any number of things that can cause that. If you were to get your eardrums both perforated, okay, that could cause mechanical deafness essentially. Okay, so if you rupture your eardrum, okay, and that can happen if you are exposed to a really loud sound really abruptly, okay, it can rupture your eardrum. Your eardrum is just a flap of skin and it will tear. Okay, and if it tears, then the little bones that are connected to the back can come off. Okay, if they don't come off, when it heals up, it'll be covered in scar tissue and it won't move as well afterwards. People that get their eardrum perforated never hear the same. Right?
Especially dangerous, like low frequency.
You know what? It doesn't. It's more just the decibels. It's not about frequency. It's just about the magnitude. If you anything over 130 will cause 130 decibels is instant perforation of the eardrum. That's really loud. That would be like thunderclap. Yeah, like a grenade goes off right next to you or something like that. Really loud. If you're at the Flames game and they score, okay, that's 100 to 110. Okay, it's pretty loud. Standing next to a jet engine when it's running, 125 to 130, it's pretty much instant perforation of the eardrum. Okay, and that's not a low frequency sound, that's a high frequency sound. It depends how close you are. If you were right at the point, it would be enough to, yeah, it would certainly. No, they're inside. They'll feel the sonic boom, but it's not necessarily so much what they hear. Well, their helmet has got, yeah, a lot of padding in it.
What happens when you shove it?
Okay, so usually what you've done there is you've hit part of the eardrum or something like that, and you don't stick it in too far because you'll go right through the eardrum. Yeah, you don't want to do that. Don't stick stuff in your ear. Okay, but yeah, that's what can happen if you go in too far. You don't need to clean your eardrum.
So
Okay.
what causes that big like that sensation like when you clean your throat, you feel it in your throat?
Pressure. So behind your eardrum are your eustachian tubes. Okay, and those are little tubes that go into the back of your throat, which is why when you're going up in a plane, you're chewing gum, swallowing, stuff like that. The swallowing motion helps to open those tubes and balance the pressure between one side and the other, right? The air pressure in your throat will be the same as the pressure outside of your eardrum. So if you're feeling that pressure, right, if you're diving or something, you plug your nose and you blow a little bit, okay, that helps to clear the eustachian tubes, help equalize the pressure on both sides. Your ears feel sore if there's a difference in pressure on both sides. Okay, so if you're coming out of the mountains, coming down, you're waiting for your ears to pop. Okay, it's because there's now more pressure on the outside than on the inside, so it's pushing in. Okay, if there's more pressure on the inside, then you feel that and you want to equalize the pressure. Yeah. Okay. You have to be careful about plugging your nose and blowing. Okay, if you're congested or anything, that can really be problematic. You're better to like plug your nose and swallow. I think that's better.
What would happen if your ears like actually?
If you perforated your eardrum, it'll bleed. Yeah. I mean, you could scrape the inside of the middle ear with a sharp object and it would bleed, but usually if it's because you were exposed to a loud sound, your ear is bleeding, you've usually ruptured your tympanic membrane at that point. Okay, so yeah, be careful. You only get one set of ears, and you'll want to hear your children laugh. And true, okay? You wouldn't want to be, at that point in your life and you can't hear your kids laugh. So yeah, think about that. All right, so we'll be looking at properties of waves here as well, guys. Okay, so a couple of things. So what's a wave? Okay, like we said here before, a wave is a traveling disturbance. Okay, to make a wave, you have to disturb something. Okay, water, air, okay, even like knocking on a door. Okay, when you knock on the door, you send longitudinal waves through the wood. Okay, you're still inducing a vibration that travels through the particles and then out the other side. Okay, it's why you can, if you put a glass to a door and put your ear up to the glass, the vibrations on one side of the door will actually travel through the particles of the wooden door, okay, and then out into the air or into the glass, and they'll vibrate the air on the other side, and you'll hear them. Okay, if you ever made one of those tin can phones when you were a kid, you guys probably didn't because you had cell phones since you were tiny, but okay, we used to build this. You put the string in between two tin cans, right? If you talk, the vibration would travel through the string. Okay, you have to it has to be tight. Yeah.
We didn't. That took us a while to figure that out. We thought it was just like a cell phone.
Yeah, because you guys are the cell phone generation. Yeah. No, and walkie-talkies and things like that were easily accessible and cheap for you. Okay. We had tin cans connected by string. Yeah, you can actually make them work pretty far. You can go from like one person's house to another, like if you were next door neighbors. Yeah. Not like two houses down or anything. But, yeah. Okay, so waves also require a medium in which to propagate. Okay, they have to have something that can be disturbed that will allow them to travel through it. So this is the example we were talking about before. We know that a wave carries energy because it's caused by this disturbance. This motorboat traveling through the water pushes and disturbs the water. That disturbance travels away. When it gets to the fisherman, his boat will be lifted up. Okay, the only way to lift that boat is to transfer mechanical energy to it. That means there was energy in the wave. Okay, the wave, that energy was carried by the wave through the medium, the water, okay, to the other person. All right, the big thing to remember here, and this is something that we miss a lot, is a wave is not a bulk movement of water like a river. Okay, in a river, water physically moves from point A to point B. Waves do not work that way. Okay, a water wave travels from point A to point B, but the water doesn't go with it. All the water does is move up and down. Okay, if that wasn't the case, all the water would end up on the land and there'd be a big hole in the middle of the ocean. Right? But that's what people think. They see the waves coming in on the beach and they see water coming towards them. That's not really what's happening. Okay? But that's what we perceive because we see the water move closer to us, and then we see it move away. Well, it's not really moving closer and moving away. It's moving up and down. So when it comes back down, like all water, it splashes. And it's the splash that kind of comes in. Okay? And when it's the other part, so that's the up part of a wave. The down part of the wave is what pulls the water back away from us. Okay.
So, like, if you're like on a cruise ship and you're in a storm,
Yeah.
is it like the water moving or is it just like muscle?
The water might move slightly, but it's circular. Wind-driven waves have kind of a circular thing to them, but they're still not really moving. Like the water's not moving. The waves are. Right? The wind causes disturbances that move through the water, but the water isn't moving. Because if that was the case and I had a big storm, okay, like a big hurricane, there'd be like a hole in the water. Like there's a hole in the cloud, like the eye of the hurricane, but there's no hole in the water, okay? They would be moving all the water outwards. That's not what happens, right? Storm surge is different. That's a pressure differential, okay? We see the ocean come in, land in a hurricane because there's a massive pressure differential that allows the water to move, okay?
So can waves like move objects? Like
Well, actually, if you watch it closely, they move only a little bit because, again, of the circular nature of the waves. When they start to curl, they can move something. But if they're just small waves, it just bobs up and down.
So is that like what an undertow is?
Yeah, kind of. Yeah.
What effect?
Well, the moon pulls the ocean one way, right? It's a gravitational thing. It actually physically moves the water. Okay, but that's not a wave, that's a tide. That's the whole ocean moving. Okay, a tidal wave, and that's the other thing. People picture a tidal wave and they say, yeah, but in a tidal wave, the water actually comes inland. And again, yes, it does, but it's because of the splash. Okay, if I get a big wave, okay, as it comes closer to the shore, okay, so here's like the deep ocean, and then as we approach, here's the shore. Okay, so what happens with the waves is a tidal wave gets created way out here in the deep ocean, right? A big earthquake happens and it pushes up on the water. Okay, it only has to push the water up maybe 1.5 feet, 2 feet, maybe more. Okay, but it's not going to move it very much. But think about how much water got moved. If it happened in the deep ocean, that earthquake, okay, it moved a whole column of water that could be miles deep up by a couple of feet. Okay, now that disturbance, not the water, that disturbance moves outwards from the point of the earthquake. Okay, so the water went up and the water came back down. Out in the middle of the ocean, that was only that far. But when we start getting closer to the shore, okay, the bottom starts encountering that disturbance more. It makes the water rear up. Okay, makes the wave get taller because the wave gets shorter. Okay, as it gets close to the shore, it slows down. There's more resistance against the bottom. So the front of the wave slows down, the back of the wave catches up to it and squishes it. And so it gets really tall as it approaches the shore. And then it runs out of water. Now, what actually happens is the wave actually moves from the water into the air. So if you were standing on the shore when the tidal wave came, which is not smart, but if you were, okay, you would actually feel like a gust of wind as the wave leaves the water and enters the air, enters a different medium. And then you'd watch that wall of water, which is now no longer supported by the energy of the wave, fall. Okay, and when it falls, it splashes. Okay? And it's the splash that comes in and destroys everything. It's not the ocean reaching out and going, and pulling all the cities in. Okay, it doesn't do that. Okay, it's this wave that's just suddenly unsupported that just collapses a column of water down and it splashes in. That's why when you see a tidal wave, guys, it just looks like a flood. I'll show you some videos of it tomorrow, or not tomorrow, on Wednesday. Okay, I'll show you some videos. A tidal wave just looks like the ocean slowly floods the area. Okay, that's a tidal wave, tsunami. Yeah, it's a type of tidal wave. Yeah.